So this is actually where we get to one of the really weird things in science, and I really am not going to try to explain it. I'll more use it than explain it. But this is the weird thing. So Bohr's model wouldn't work for a lot of atoms. Basically everything except hydrogen. Hydrogen it worked for, and everything else it didn't work for. The question is what was wrong with his model? See, what Bohr never said was, why do these energy levels exist, right? And it turns out that the reason they exist is because electrons have wave-like properties. So think about what I just said, right? Electron is definitely a particle. It's like a dot. But at the same time, when we look at how they behave in atoms, their behavior is really wave-like. And if you think about a wave, if that was an electron, right, it would be superimposed amongst many different positions in this wave. That is, it would be, if the electron was a wave, it would be all of this wave. So it has many, many different positions. And then if it's a particle, it only has one position. The energy of a wave, right, is defined by its wavelength and its frequency. And so it turns out it's this wave nature of an electron which explains why these energy levels exist. Now, if you want a more thorough explanation, you're going to end up having to take more classes in either chemistry or physics, and then you'll maybe finally be happy. People have famously said, Richard Feynman has famously said, if you think you understand quantum mechanics, you don't really understand quantum mechanics. Schrodinger, who designed the equation, we call it the wave equation, which describes the electron's wave-like behavior in atoms, was so disturbed by this superposition of states, that an electron is both a particle and a wave, that he stopped studying physics and went into biology. So, I mean, yeah, so it's caused extreme reactions in science, and in essence, we do actually know a lot about the particle wave-like behavior, but it's still something that people have difficulty sort of grasping a hold of. Okay, this video that's here, okay, this YouTube video is a video put on by the Royal Society, and it's somebody sort of describing the wave particle behavior and how odd it is. And so if you want to catch a video and sort of get a background on it, you might want to type that address in and watch it. I shortened it up so it's a bunch of weird letters. I shortened it up so it's a little easier to get to. Now, remember I said at the very beginning, at the title of this module, it has to do with whether or not the cat is dead and alive. And this is actually a classic problem in physics. And Schrodinger had a cat, and he stuck it in a box. I spent a little bit of time tonight, because cats really like boxes. If I put a box down, a cat will go sit in it. But we threw all the boxes away, and so I only had a really small box, and they wouldn't quite fit. So Schrodinger's got this cat, and he sticks it in a box, and he seals it up in a room. And he seals in the box with the cat radiation source. And the question is, sometime later, is the cat dead or alive? And for us, the cat is either dead or it's alive, right? And when we go to open the box, we will know whether or not the cat is dead or alive. But what Schrodinger said, and this is the superpositions of states, until you look inside the box, the cat is both dead and alive. Now, it seems ridiculous to think about that for a cat, and it kind of is, but it turns out for an electron, it is exactly that way. You can have an electron in a system, and it'll behave, right? You don't know how it's behaving. As soon as you look at it, it behaves as an electron, like a particle. But if you leave it to do things on its own, it does all the things you would expect a wave to do, like being in two places at one time. A lot of modern electronics is based on these superposition of state ideas. So computers, LCD monitors, all kinds of stuff. So it's a very important topic. But the idea of the cat being both dead and alive is something that most people find pretty disturbing, right? Okay, it's like zombies, right? Anyways, in the next section, we're going to sort of forget that. We'll talk about some of the outcomes of quantum mechanics. So, for an electron, the wave-particle duality is what it's called, but its wave-like behavior results in a thing we call uncertainty of position and uncertainty in momentum. Momentum would be the energy and direction the particle is traveling, and position would just be we don't know exactly where it is within this space. So this has some really weird effects on how we think about an electron. First of all, there's a picture of a baseball player, right? And a baseball player is going to swing a bat where he thinks the ball is going. And he judges based on the speed, probably based on what he knows of the pitcher and what the pitcher likes to do. He makes a best guess as to where the baseball will be. Now, there is a strike zone, right? So if he thinks he's throwing a strike, he's going to say most likely that that ball is going to end up in sort of this region that's in here. Oh, maybe that's not the best color. Let's try this one. And that region right there, right? That's the high probability region for the baseball. And the baseball is definitely a particle. It's something you can see, right? But now the electron is, so baseball is definitely a particle. It behaves like a particle. And whether or not it behaves like a particle or wave has a lot to do with the size. And so an electron is really small, and it's going to behave like a wave. And when we think about where will the electron be, right, we have a region of space, just like we have a region of space where the baseball player thinks the ball's going to be, we have a region of space where we believe the electron's going to be. So unlike Bohr's model of these lines that go around in space, because those are very distinct regions, it becomes a fuzzy region, and that fuzzy region is what we call an orbital. So we went from orbits in Bohr's model to, in the quantum mechanical model, we start calling them orbitals. Now, what they did in this diagram is they just took and said, it's a computer simulation. Where is the electron if we stop it right now? Where is the electron if we stop it right now? And it fills this space up. The highest probability region of finding an electron is always around the nucleus somewhere because of the opposite charge and the attraction towards each other, right? Now, these orbitals are defined by mathematical equations, and as a result, these mathematical equations have some very unusual properties in terms of their shape. Now, we call these orbitals S, P, D, and F, okay? And the letters come from the spectroscopy. Remember we talked about line spectra. They come from the spectroscopy of the lines that are produced by these different kinds of orbitals. So sharp and fine, diffuse, I think P was principal. These were the letters that were associated with the shapes of the lines, and it turns out these shapes of the lines actually dealt with different kinds of orbitals, or can be associated with different kinds of orbitals. So an s orbital, thankfully, looks like a sphere. Now, I can't draw a sphere very well, but let's just do it like that. It's got shading on one side, right? It looks like a basketball. And that's exactly what we think an atom looks like in our head, right? Because we have Bohr's model. It's round, it's spherical, right? The electron's in the sphere. But again, this space is like this space here. There's an XYZ axis. It's spherical in nature. There's a probability of finding the electron in that space. Now, remember we talked about energy levels, right? At every energy level, we can have different orbitals. And so one of the orbital types, which you can find starting on energy level 2, right, second quantum number, is this one. And maybe the best description for that would be two balloons that are tied together at the bottom. So if I were to put shading, right, the shading would be down here, and then the shading would be down here, something like that. And then there's d orbitals, and d orbitals look like this. That's not really the best drawing, but let me see if I can do a little bit better for you. They're starting in the middle, and they're sort of like this. So what does it look like, right? It kind of looks like a flower with 4 petals. Well, that's kind of what it looks like. But again, these are like balloons. If I took 4 balloons and tied them together and flattened them out, that would be one of the d orbitals. Now, they're not all shaped like that, but most of them are shaped like that. And an f orbital is actually 3-dimensional. So I don't know if you know what a chrysanthemum is. It's that big round flower that you can get with lots of petals. Well, what's going to happen in an f orbital is you'll have this shape, right? But you'll have one set in the front, one set in the back, and they'll be tied together in the middle. I'm not even going to try to draw it. Look it up, okay? You'll be surprised like how weird these things actually look, and people have spent a lot of time trying to come up with what these shapes have looked like. Now, having said that, you can't actually see these because all they are is equations describing the probability of where you find the electron. Okay, so now, let's go and break some of this down, and we're going to talk about the kinds of orbitals you can have at any of the principal energy levels. Okay, so remember, back here, we talked about n equals 1, n equals 2, n equals 3. These are the quantum states, or the quantum levels, or principal energy levels, right? Quantum numbers. As you go further out from n equals 1, n equals 2. So I drew these for the ground state being at the very bottom and going to higher excited energy states for a hydrogen atom going up. So if I'm thinking about n equals 1, it's a low energy orbital or energy level, and it has one orbital type in it, and that would be the 1s orbital, like that. Okay. Now, it turns out when you get to energy level 2, you have a 2s, and then you have 2p orbitals that look like this. And when you have the 2p's, right, there's 3 of them, and each one of them looks like that dumbbell shape, but it's oriented in different directions, like x, y, and z directions, okay? So think about it like this. If you were going to a hotel, right, and it was a small hotel at the bottom, and you walk in, and there's the desk for the clerk there, and your office, your room was right next to the clerk's room, right? That would be the 1s, the cheap seat, the lowest energy level seat that cost you the least amount of money. Now, you go to the second floor because you got a little bit more money, a little bit more energy, right? You can get the 2s, which is like the 1s, it's near the elevator, or you could get like the 2p's. The 2p's will be a little bit more energy, and there's 3 of them because they want to make a little bit more money, right? And it turns out this is how the orbitals lay out. If you start at the bottom, you have one cheap room. You get to the next level, you have one cheaper room, but you're the energy level up, so you're not right where everybody walks in. And then you have 3 more rooms that cost a little bit more money because they're not next to the elevator. Okay, now, think about it like this. You go up to the next one, you go like this. There's 3s, and then there's 3p. Again, these are slightly higher in energy. In hydrogen, they're all the same, but in most atoms, they're slightly higher in energy. Cost you a little bit more money. And of course, the hotel wants to make more money, so they have these d orbital rooms. And it goes like this. So let me condense that a little bit because I went a little bit crazy on the size. I'm going to run out of space, so let me condense this. I'm just going to go like this. So 3p and then 3d. I put lines in the middle like this so I can see like where one starts and one stops, right? So I'd have lines in here like this as well. Now, um, there's a pattern to the number of each type of room. The cheapest rooms, there's one. The S's, there's one. The P's, there's three. Right, and the D's, there's five, so it goes by odd numbers, 1, 3, 5. So the F's would be 7. So you go one more floor up. This would be the 4S. This would be 4P. This would be 4D. And there's also a 4F. And there's 7. I think I got 7 in there. Now, it turns out there's, if you go to energy level 5, right, you think, well, there's 5S, 5P, 5D, 5F, and then what's after that, right? Shouldn't there be like another room? And there is another room, but it turns out there are no occupants ever in those rooms in the ground state. That is, if the hotel was full, they would not even fill those rooms. So we don't usually talk about them, but the next orbital over is the G. So over here in the space that I didn't leave room for would be the 5G orbitals, but over here we'd have the same, the 5S, the 5P, the 5D. By the way, you don't have to memorize this, right? And then the 1, 2, 3, 4, 5, 6, 7, the 5Fs like this, okay? And each room is double occupancy. You can get 2 people in a room. So in the 1S, you could have 2 electrons, like 1 electron or 2 electrons. Okay, and we'll talk about how that happens. And then the 2S, you could have 1 electron or 2 electrons. And the 2P, you could have 1, 2, 3, 4, 5, 6, because each one could hold 2. So each of these orbitals, each of these rooms, is double occupancy. Okay, so this is like Hotel Calgoa. You probably would never stay there because it'd be all about chemistry. But this is the idea. The gap in energy between 1S and 2S, the way I've drawn it here, is actually bigger than 2S to 3S. Not that important for you to know that at this level, but I just wanted you to know that, okay? So that's the transition, like the introduction to quantum mechanics we did, and then the transition from orbits to orbitals. And next what we'll talk about is how we fill those rooms with electrons. And they call those things electron configurations.